This is the 30th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video discusses the fetch-execute cycle. The previous two videos took a close look at the format of a machine instruction and how the CPU executes that instruction. The final thing we need in order to run a sequence of instructions is a mechanism for supplying new instructions once the current instruction is complete. So before we see exactly how to do this, let me add a little bit of context. The type of CPU we're building is what is known as a single-cycle CPU. That means, 1, the CPU only processes one instruction at a time. It completely processes the current instruction before beginning the next. This is kind of like saying the instructions have to stay in a single file line. Also, each instruction is completely processed during a single clock period. So when you put those two together, this means that exactly one instruction is completed every time the clock ticks. The benefit of a single-cycle CPU is simplicity. Later in the semester, we'll see how moving away from the single-cycle model allows us to make the CPU much faster. But for now, with the single-cycle model in mind, we need a mechanism for supplying a new machine instruction on every clock tick. So the first thing you need to know is that instructions are stored in RAM. Conceptually, you can think of RAM as a big array that holds data. In this case, the data is the list of instructions we want to execute. We access this data by providing as input the index of the item we want, although with memory we call it an address rather than an index. The RAM responds by returning the data at that location. This is, in many respects, like accessing an array. In MIPS, RAM is what we call byte addressable. This means that each input refers to 1 byte, or 8 bits, of data. But, if you remember, MIPS machines' instructions are all 32 bits long, which is 4 bytes. So even though a RAM address technically refers to a single byte of data, the hardware will return 4 bytes when accessed. So you beginning to see the appeal of hexadecimal here? Anyway, the size of the address depends on the amount of data you want access to. Since we will eventually be using our ALU to calculate memory addresses, it's convenient to make this address the same size as our word, 32 bits. This is yet another example of how the word size affects other CPU design decisions. Using a 32-bit address means that we can address up to 4 gigabytes of RAM. That annoying asterisk there? That's the virtual memory chapter crying for attention, but it's going to have to wait. For now, you can pretend that RAM is implemented like a huge register file, but realize the truth is much more complicated and actually much more interesting. That is a topic we may or may not have time to cover this semester. Alright, for the rest of the video, I'm going to represent RAM as simply a blue box that has one input and one output. The input provides the address of the desired instruction, and the output contains the instruction itself. To keep things simple, we'll make sure that addresses are always a multiple of 4. Once outside RAM, the instruction is split up and sent to the various CPU components as we saw in the previous video. The question now is, where does this address come from? The current instruction's address is stored in a special purpose register called the program counter. The sole purpose of the program counter is to keep track of which instruction the CPU should be running. The program counter is called a special purpose register because it can only be used for one thing, for one special purpose, keeping track of the current instruction. In contrast, the registers in the register file are called general purpose registers because we can use them for just about any purpose we want. Most instructions make use of them, and there really aren't any limits on the type of data we can put in them. This is notably different from special purpose registers like the program counter that can only be accessed by very specific instructions. So now that we see where the instructions come from, let's walk through a complete clock cycle and see how that instruction is fetched, executed, and the next instruction fetched. Well, actually, before I do that, let me quickly point out a new notation. If you see a small triangle on a component, that means the component takes the clock signal as input. We use this convention to avoid cluttering up the diagrams with clock wires. The key thing to notice here is that the program counter is clocked. And because it's clocked, when the clock ticks, the program counter gets a new value, the address of the instruction that should be running during this clock cycle. the RAM receives this address as input and then returns the instruction to be run as output. At this point, the instruction is unbundled and the different fields are sent around the CPU, which then executes the instruction as described in the previous videos. At the end of the clock cycle, the ALU result should be on the register file's write data input. At the same time all of this is going on, there's also a separate adder that calculates the address of the next instruction. Notice that this adder has a hard-coded input of 4 because every MIPS instruction is exactly 4 bytes, 32 bits, long. This value, which represents the address of the next instruction, is ready and waiting on the program counter's input by the end of the clock cycle. So now, when the clock finally ticks, both the ALU result and the new instruction address are saved in their respective registers, and the process begins again. The next instruction is executed, the instruction after that is fetched, and so on. This process of fetching and executing instructions is called the fetch-execute cycle. Okay, so let's summarize. Instructions are stored in RAM, something we often informally call memory. The program counter is a special purpose register that keeps track of the current instruction's address. We say that a register is a special purpose register if it can only be used for a very specific purpose. Registers that can be used by most any instruction to hold whatever data is needed at the time are called general purpose registers. In a single cycle CPU, while the CPU is executing an instruction, it's also computing the address of the next instruction at the same time. This process of fetching an instruction from memory and then executing it is called the fetch-execute cycle. In the next video, we'll see how machine instructions are created and loaded into memory.